All right, guys, chapter 10. Chapter 10, really interesting. So you see the title there, Taylor Polynomials and Infinite Series. We are going to take calculus in a whole new direction with a whole new purpose in this chapter. And what's interesting, we're really going to get a glimpse at how calculus gets used when it comes to our technology, and how calculators even think in terms of some things that are very familiar to us. Our calculators think about them in very different ways. And then, you can imagine, um, you know, more advanced technology, really takes that same idea to a whole other place. So I will give you some insight into that as we go through the first section. But turns out we've got a couple of prerequisite things we want to be familiar with, remind ourselves of before we even get into the section. So chapter 10, Taylor Polynomials and Infinite Series. The first thing to look at as our prerequisite is higher order derivatives. So far in Math 121, Math 122, the highest we've done is the second derivative, right? We've never taken it further than that. And not that that probably sounds very surprising that you could take a third derivative or a fourth derivative, but let's just take a look at it. Turns out there's some notation there we want to be familiar with. So let's take a look at this example. F of x equals the square root of 2x plus 1, but of course we want to think of it as 2x plus 1 raised to the 1/2. So our first derivative, well, we've got a chain rule, right? So the 1/2 comes down, we multiply by the 2. Okay, the 2 and the half cancel, and our first derivative is simply 2x plus 1 raised to the negative 1/2. All right, let's look at the second derivative. Well, again, we've got a chain rule, and multiplying by 2, the 2's cancel out. So we have negative 2x plus 1 to the negative 3 over 2. Okay, hey, why stop there? Let's look at the third derivative. We'll call it f triple prime of x. And going again, well, the exponent multiplies down, positive 3 over 2 to the negative 5/2. The chain rule again, we get positive 3, 2x plus 1, raised to the negative 5 over 2. Let's go one more, a fourth derivative. And you notice when we take the fourth derivative, we no longer write 4 prime marks. And I think everybody agreed at some point that 3 is about as much as the eye can, distinguish. Once you get to 4, it starts getting difficult. So instead, we write this tiny set of parentheses and a 4 there to indicate the fourth derivative. You might think, why the little parentheses? Well, if the parentheses were not there and we just had the 4, it might look like an exponent, like raised to the 4th power. So the little parentheses make clear it's not an exponent, we mean a derivative. So, okay, the fourth derivative, well, okay, let's do it, right? Multiply that down, negative 15 over 2, negative 7 over 2, chain rule. Okay, we end up with negative 15 times 2x plus 1 raised to the negative 7 over 2. All right. You could keep going here. There's no reason to stop at the fourth derivative, but I think that makes the point. Okay, next. Now this is more like review material. Might have been a while since you've thought of factorials. Factorials come up usually in an algebra class when you talk about sequences and series. But that maybe has been a few years. So let's check out this. The exclamation point you read as factorial. So that is 5 factorial. If you look closely at your calculator, you might find a factorial button. Maybe it's under some options. Maybe it's just right there. Anyway, what does this mean? 5 factorial. So you start with the number, and then you count down until you get to 1, the whole numbers. and you're multiplying them. So 5 times 4 times 3 times 2 times 1 is 5 factorial. And it so happens that when you multiply those numbers, you get 120. So here, 5 factorial equals 120. There's one kind of odd case when it comes to factorials, and that is 0 factorial. And for a moment, you're like, what does that even mean? Like, I can't even, 1 factorial. Well, I would just start right there and I wouldn't do anything. 1 factorial would equal 1. How do we do 0 factorial? Well, by definition, we want a value for 0 factorial, and turns out we just say it equals 1. So it doesn't fit the pattern of the other numbers. So just by definition, 0 factorial equals 1. Okay, the last part of our review, our prereqs, is summation notation. Okay, so I'll give you an example here. Again, in an algebra course, sequences and series, you may have seen this giant Greek letter sigma. Below the sigma, you're given some variable. We're going to go with k. Sometimes you see other variables there like I or n. But let's say k equals 0, so that tells us where to begin, and the number on top tells us where to stop. So begin at 0, stop at 5, and then they're telling you the expression that you're going to plug those numbers into. So maybe, for example, 2k plus 1. The sigma tells us we're adding. Sigma s, the Greek letter s, stands for sum. Take the sum. So we're going to plug in 0, and then we're going to plug in each other number counting up to 5, and we're going to add all those together. So plugging in 0 gives us 1, plugging in 1, plugging in 2, plugging in 3, 4, and 5 gives us all of these numbers here, and then the sum tells us to add them all up. So 1 plus 3 plus 5 plus 7 plus 9 plus 11, I hope I did my math right, is 36. So that's what that would equal in the end. But really, I just want you to, it's not so much what it's equal to that's important. It's just what do these symbols even mean, right? Okay, we are ready. Let's start 10.1, Taylor polynomials. Okay, what's the idea? What is so interesting and new and applicable about Taylor polynomials? We're going to approximate any function with a polynomial. Any function. So I'm talking about e to the x, natural log of x, sine of x, cosine of x. Why stop there? How about, square root of 2x plus 1 we saw in that example a few minutes ago? We're going to get a polynomial. What does it mean to approximate it? If you were to graph them, they would have almost identical graphs, at least over a certain domain. Okay, this is crazy. So we're going to take a look here, and then at some point I'm actually going to pull up Desmos on my computer, and I'm going to grab the camera and kind of show you what's going on. Okay, let's look at an example here. The classic example is e to the x. So it turns out we're going to approximate this function e to the x with a polynomial. And you'll see it, the best way to see it is in the graphs. What we're going to see on the paper isn't going to be exciting or convincing really until you see it graphed. We need some place to center it. We're going to center at 0. That's going to be a really good spot to start us off. And we'll explain just what that even means. So centered at a equals 0. What does that even mean? Okay, and you really see it when you graph it. Okay, let's go through this example. Here's what we need to do. I'll just show you all this. We are going to take several derivatives of our function. So we start with the original function, and then I decided to take 3 derivatives. And we could do more, but I think 3 will make the point. So the original function, and then what's great about e to the x, right? Its derivative is the same, of course. So first derivative, second derivative, third derivative. Now here's where the centering at 0 comes in. we're going to plug 0 into each of these 4 functions and find their value. So f of 0, f prime 0, f double prime 0, f triple prime 0, and of course they all come out to 1. Again, that makes e to the x a really simple example for this. Won't always be the case. And now here on the side, this is just some of the language that we use so you can start to get familiar with it. So that original function, we call that degree 0. The first derivative we call degree 1. The second derivative is degree 2. The third derivative is degree 3. So the degree is really telling you how many derivatives there are. Okay, and we begin at degree 0 because there's no derivative at the beginning. Okay, here's how this works. We're going to take these 4 values right here, and we're going to plug them in to this pattern. And it is like a sequence or a series. So I'm going to try and keep this on the screen. Okay, well, I bet we can fit everything for now. All right, so the original function, e to the x. That function will be approximated by, and here's the pattern we're going to follow. And you see it has powers of x, it has factorials, and it has these numerators. Okay, here's how it works. So these numerators are actually the 4 numbers we just calculated. They all happen to be 1, but this one right here that goes with degree 0, that is this first numerator. It's over 0 factorial, x raised to the 0. This one right here gets added on. So that's 1, now it's over 1 factorial, x to the first. This one right here for degree 2 goes in that one over 2 factorial, x squared. And this one is that one right there over 3 factorial, x to the third. And if you thought about it, hey, what would be the degree of this polynomial? And you would look at the highest exponent. This polynomial has degree 3. So they kind of like, that's where the names come from. Now, of course, we can simplify all of this nicely. And so I'll go ahead and slide it up a little bit for you. But our same function, e to the x, is going to be approximated by, and let's clean these up. Okay, well, we got 1 over 0 factorial is 1. X to the 0 is 1, of course, so that's all just a 1. The next one, 1 factorial is 1, so this all just works out to be x. 2 factorial is 2, right? 2 times 1. So this is 1/2 x squared. And 3 factorial is 3 times 2 times 1. So that's going to give us 1 over 6 x to the third. Okay, now I'd like you guys to kind of play this out with me. If you've got, obviously you've got your computer there if you're watching this. Bring up Desmos, and I want you to compare the graphs. I'll do it on my computer too, but even better if you do it along with me. Graph this, and then we'll end up graphing this whole thing, but we're only going to do it a piece at a time. And we're going to have both those graphs up on Desmos at once. Okay. So let me try and work this out. Let's see, I'm going to adjust my camera here so I can maybe tell kind of what's going on, make sure it's on the screen properly. Okay. All right, there's my computer screen. So I have graphed e to the x, and I'm kind of playing with it, get it to look nice. Looks like I was pretty well zoomed out. Okay. That is simply e to the x. Right? So here's what I'm going to do. Over on the side here, so there's my graph e to the x. I'm also going to graph that 0 degree, just the y equals 1, just the first term of our answer, right? So y equals 1, well, that's not very interesting, but it does cross the same point at 0, right? And we'll kind of see this, the centered at 0 come out here. So it has the same y value at 0. Now I'm going to add the next term, and all it was plus x. Okay. And what happened? Ooh, it still goes through that same point, but now the slope is even the same as e to the x. And it's still just a line. So you think, hey, does this line approximate that graph of e to the x very well? Well, no, but when you get near 0, yeah, that's not bad. It's not bad. Well, it's really just a tangent line at this point. That's really not all that interesting. Let's add the next term. What was it? 1/2 x squared, right? And you look at that and you go, wow, 1/2 x squared. It goes through the same point. It's got the same slope as e to the x, my red line, and it has the same concavity right there. The second derivative matches. So the original function, the first derivative, and the second derivative all match at 0. As you start getting further away from 0, it starts to, there starts to be a big gap between them. But when you're near 0, oh, it's really, really good. Hey, we got one more. We're going to add on 1/6 x to the third. And wow, I mean, it's better every time. So now, I mean, up to 3 derivatives all match right there. And yep, as you get further away, as you get down to around -2, there starts to be a pretty big gap here. On the right side, though, that holds really well for quite some time. But certainly near 0, that is very accurate. So if you were to plug in an x value near 0, into our answer, you're going to get a number that's very close to e raised to that number. Okay. Let me pull it back here, and that was the point I was trying to make. So what's the usefulness here as we wrap up this first video? I'll give you a little bit of insight. So turns out technology, your calculator has no idea what e to the x is. There's a button for e, but it's not thinking of it the way that humans do. It's thinking of it as this Taylor polynomial, and actually it would have many, many more terms if we kept taking derivatives and kept following the same pattern that we've got above. And so it's able to get a very high degree polynomial to approximate something that is not a polynomial. I mean, that's really, really cool. Why polynomials? Why would we want our computers to think in terms of polynomials? So it turns out polynomials, very easy to take derivatives, very easy to take antiderivatives, integrals, right? Very easy to plug numbers into, right? I mean, this has what e is, what 2.71 something something some very difficult decimal number, and then raise that to a power. We don't want our calculator to have to think about that. We want our calculator or our computer just to plug a number in and have this like squared, cubed, easy, right? And so that not only goes for e to the x, but when our calculators do sine of x, cosine of x, tangent of x, natural log of x, all that sort of thing, they're using a Taylor polynomial. Okay, well, let's conclude video number 1 here. We're going to get into some more examples in the next videos.